We're going to solve some trig problems here, trig equations that are going to involve arc sine or arc cosine or arc tangent. But before we can apply any of those arc relations, we have to do some other work, either algebraic work to get it to a position where we can apply them, or in some cases some trig identities to help us solve the problems. This first problem, we're supposed to find the theta intercepts on this graph in this domain from 0 to 720, and this graph, this is 720 right here. So we're looking at the whole picture. It looks like there's 4 solutions. It looks like it just touches in these spots right here and here and here, and we'll see if that's true or not. Well, there. We'll see if that's true when we do this algebraically. Now you look at this equation. This is the equation of this graph, and it doesn't look like a sinusoid. It's got some extra little bumps, and it doesn't have that smooth regular curve of a sinusoid. When you look at the equation, it looks like, hopefully you're thinking, hey, that kind of looks like a quadratic equation. It looks like it's in the form ax squared plus bx plus c, except instead of having an x, we have a cosine theta. One way to deal with that is to choose some variable. I'm going to choose, let z, and this can be any arbitrary variable you want. Don't use y, maybe don't use x, but z is a good choice here. Let z equal cosine theta, and then we can rewrite this equation as 6z squared plus 7z plus 2. Now you don't have to do this, but for some people it makes it easier to just think about the quadratic part of this. And we're looking for theta intercepts, so that's when y is equal to 0. So we set this equal to 0. Now, we have good quadratic techniques that you've learned over the years. One is factoring, another is the quadratic formula. Those might be the 2 main strategies that you think of. Oh, this is z squared. I happen to know that this is factorable. Maybe you can factor this easy. One, it could factor like 3z and 2z. And then I would have to have a 2 here and a 1 there in order to get the constant value of 2. And make sure when you're done with this, make absolute sure that this is the correct factorization. So 3z times 2z is 6z squared. 3z times 1 is 3z plus 2 times 2z is 4z. 3z plus 4z is 7z. 2 times 1 is 2, so that all works out. And here's a little algebraic reminder. Remember, the reason that we are so interested in factoring and setting something equal to 0 and then factoring is because there's this multiplication property of 0, which says if a times b is equal to 0, the only way that can happen is if either a is equal to 0 or b is equal to 0. So that allows us to set each factor equal to 0. So we get 3z plus 2 equals 0, or 2z plus 1 equals 0. And those are nice, simple linear equations that are easy to solve. Well, at this point, it'd be a good idea to replace z with cosine theta, because remember, we are not particularly interested in what z is. We really want to know what theta is. Oops. So rewrite this in terms of cosine theta again. You don't even ever have to use the z thing, but like I said, it sometimes is helpful to people. Okay, now we have an equation that looks like we could apply the arc cosine to these equations. So I'm going to subtract 2. I get 3 cosine theta equals negative 2. Cosine theta is equal to negative 2/3. And theta is equal to the arc cosine of negative 2/3. And that would be theta is equal to plus or minus, because remember, this is how arc cosine works. Arc inverse cosine of negative 2/3 plus 360n this would be a good time to get out your calculator and figure out what the inverse cosine negative 2 divided by 3 is. And it's that, and I'm going to store that. I think I'll want to use that later in alpha A, 131.8 degrees. So 131 plus or minus 131.8 degrees plus 360n. Let's leave that there. That's a nice general solution for that part. And go back to this one and do the same thing. Solve the equation for theta. Negative 1 cosine theta equals negative 1/2. Theta is equal to the arc cosine of negative 1/2. And I hope that's supposed to be 2 there. I hope you're all thinking, I recognize that negative 1/2. I've seen that on the unit circle before. Well, you would be right, and you don't really need to get out your calculator now, do you? You can solve that by thinking about the unit circle. So that would be plus or minus 120 degrees and plus 360n. So now we have these general solutions from both parts, from both factors, and they both should produce solutions to this equation. Let's take the one on the left and find all of those first. Let's try and do this in a semi-organized fashion. So we don't want negative 131.8, but we do want 131.8. So that's one solution. Plus 360 would give us another one, 131 and 491. If I add 360 to that, too big. Okay, so I got from the plus 131.8, I got 131.8 and 491.8. I'm going to write those down. 131, if I can remember. 131.8, and I hope the other one was 491.8. So that's 2 of them. Let's look at negative alpha A. That would be negative 131.8 plus 360. Okay, 228.2 plus 360. And that is going to be 588. And if I add 360 to that, that's going to obviously be too big. So 228 and 588 are 2 more. 228.2, 588.2. Write those down. 228.2 and 588.2. So here's 4 solutions. And then from this, we don't want negative 120, but we do want positive 120. And 120 plus 360 is 480. We want that. And if I add another 360, that's going to be too big. Negative 120, we don't want. But negative 120 plus 360 is 240. We want that. And 360 plus that is 600. So I did that in my head, and you could do it on your calculator, but I think I got it right. I think I will rewrite these so I get them in numeric order just because it's a little bit nicer to read. So these are my solutions. Let's see, what's the next one? 228.2, 240. So I got that one, that one, that one, that one. 480. 491.8, 588.2, there's a 1 in there, and 600. Okay, so those are all the solutions. And one thing you might observe here is there weren't 4 solutions, there were actually 8 solutions. So it looks like it's touching, it looks like the graph is touching down there, but it's actually dipping just ever so slightly below and intersecting in each spot twice. So there's actually 4 solutions there, and then over here there's 4 more solutions, so there's a total of 8 solutions. So your graphs can be deceiving. You can't necessarily read it off the graph always very accurately. But our algebraic solution, we definitely got all the right solutions this way. Okay, we could use second calc intersect to check those solutions or find them that way, and you know, confirm that this is all good. Although, you know, going in and finding the intersection point might be a little bit tricky because they're so close together. Okay, that's example 1. Here's example 2. Now this one also has a squared term in it. A couple things that make this a little messier. It's in radians, that's okay. We want to find the solutions between 0 and 4 pi. That's great. But in this case, not only is it something quadratic going on, but we also have both sine and cosine in the same equation. Now, could we rewrite this so that we have just sine or just cosine? Well, I know an identity that allows me to rewrite cosine squared, but I don't have one for sine x. But I do have one for cosine squared x. So what you do is you take this cosine squared and you rewrite it. Remember that cosine squared is equal to 1 minus sine squared. 1 minus sine squared x. Make sure you use parentheses here so that you distribute things and get everything right. Okay, so I get 5 minus 5 sine squared x plus 3 sine x equals 1. We want to set this equal to 0, so negative 5, I want to write this also kind of in ax squared plus bx plus c form, plus 3 sine x, and I subtract 1, I have 5 minus 1, which is plus 4, equals 0. All right, and I don't think I want to, maybe this is factorable, but let's do it with a quadratic formula. So hopefully you have a quadratic formula program on your calculator to make this easier. Now remember, in our quadratic formula, the results are going to be the values that sine x is equal to. These are not our answers. They are what sine x is equal to. And then we have to apply arc sine. So negative 5 for A, 3 for B, 4 for C. I get these two solutions. These over here so I can remember them. So now remember, that's what sine x is equal to. So sine x equals negative 0.6434, or sine x is equal to 1.24, 0.2434. All right, now these I can solve with arc sine. Well, hopefully you're picking up on some things here. Hey, you can't have a sine value bigger than 1, so we don't even have to deal with that. That just goes away. Anytime you see a sine value that's bigger than 1, you can just cross that out. This one I need to do x is equal to the arc sine of negative 0.6434. I'm in radians. Oh, I better change my mode to radians. Here I go. Change to radians. Take the, by the way, you know, your program stores, the first value is stored in X and your second value is stored in Y. So you can actually use those stored values when you do this, which will make your answer more accurate, and we love that. So the arc sine of alpha, well, you can just use X. of x, because that's where the negative 0.643398 is stored. Inverse sine of that x value is that angle. That's our first angle. So negative 0.6989. Negative 6.6989 plus 2 pi n. That's one value for x. And remember how you do arc sine. The other one is going to be pi, because we're in radians, minus that value we just found. So I'm going to use second answer. And this should, so my angle should be in the third and fourth quadrant. That 0.6989 is an angle in the fourth quadrant, and this angle 38405 is in the third quadrant, right? That's bigger than pi. 3.8405. So that's my other one. I can't remember that, so I'm going to put that over here so I can look at it. And so here are my solutions for x, my general solution, 0.38405 plus 2 pi n. And I'm supposed to find solutions between 0 and 4 pi. Well, once again, I've got some values that are not between. The negative 0.698 I don't want, but I do want that plus 2 pi n. So let's start with that one. I should have stored that value. I'll just redo it. Inverse sine of x. Give me that. Don't want it, but I do want that plus 2 pi. Plus 2 pi. 5.58 plus another 2 pi. See if that's still less than 4 pi. 4 pi is 12 something. So 11.86 is smaller than that. So those two solutions are good. Again, I'm going to put these over here so I can look at them. And let's find the ones for the other solution. 5.584. No, that's not it. 3.8405 is one solution. Do want that. And then I want that plus 2 pi. And if I had another 2 pi, that's going to make it bigger than 4 pi. Because 4 pi, just to confirm that, 4 pi is 12. And if I had another 2 pi to 10 point something, it's going to be 16 something bigger. So, what was that? 10.1236. 1237. Okay, so my solutions are 5. Well, let's write down the first numeric one. Put this in numeric order. First one is 3.8405, and then I've got 5.8. Can't write. 5.5843, and then what was another one? 11. 10.123 and 11.8674. Now, of course, you can put this in your calculator and graph this thing and check those solutions. I'll let you do that. Check my solution, see if I got it right. It's always a good question. Okay, one more problem. I don't want to make this too long, but here's one more problem. This one involves tangent And this one's not so hard, seems simple, but there is an algebraic, something to watch for algebraically. Let me just do you a little algebraic equation as an example of how not to do this and why. If I have an equation like this, let's say I have 5x or something like that. That is a quadratic equation. And in a quadratic equation, you're expecting to see two solutions out of any quadratic equation, unless there's a double root, you know. Okay. If I divide by x on both sides, this is what not to do. If I divide by x on both sides, I get 3x is equal to 5, and then I would get the solution x equals 5/3. But this equation is a linear equation, and it only has one solution. So by dividing by x, I changed the degree of the equation from a quadratic equation to a linear equation. Quadratic equation, you're expecting two solutions. A linear equation, you're only expecting one. And the solution that we're missing, of course, it should be clear in this problem, is that x is equal to 0. Well, you can't divide by 0, so you're essentially eliminating a possible solution by dividing out a variable. So that is an algebraic no-no. So how do you avoid that? In this case, what you do is, like in the other quadratic equations we had, quadratic situations, we subtract and set this equation equal to 0. And in this case, you should definitely choose the method of factoring. Factor out a tangent theta. And you get tangent theta times tangent theta minus 2 equals 0. And as we did before, when we would use the factoring technique on the first example, you do tangent theta equals 0 and tangent theta equals 2. And now we can use arctangent to solve these things. So theta is equal to the arctangent of 0. Oops. Arctangent of 0, and theta is equal to the arctangent of 2. Now the arctangent of 0, as you probably know, is equal to 0. So that would be 0 plus 180n, which is just equal to 180n. And this one would be equal to the inverse tangent of 2 plus 180n. And we're doing this in degrees, so I'm going to change my mode again. I'm going to back to degrees. Make sure you do that. Inverse tangent of 2 is some angle in the first quadrant, like 63.4 degrees. 63.4 degrees. 63.4 degrees plus 180n. I want solutions between 0 and 360, and you notice that this has a square bracket there. That means theta can be greater than or equal to 0, but less than 360. And the reason for that is I don't know why they did it in this case, because the tangent of 360. The tangent of 360 is 0, so it would have a solution. I was thinking the reason they did that was because it would be undefined there, but it's actually not. But we'll just go with what they say. So we don't want 360 as a solution. So we want 0 and 180, and we want 63.4, and we want 180 plus 63.4, which is, I hope, 243.4 if my addition is correct. And I didn't put this in numeric order because I want this podcast to be over right about now. So thanks for listening, and I hope these examples are helpful to you.